sections I hope to cover today, and that will be the homework 1 through 8. Radiation is just magnetic field and an electric field oscillating at right angles to each other and at right angles to the direction they travel. All electromagnetic radiation is the same thing. The only difference between one and another is the wavelength and the frequency. You need to be familiar with the electromagnetic spectrum and the difference. Here's a picture of it. Notice that visible light is just one small piece of the electromagnetic spectrum. We start with gamma rays down here, so high energy on this end and lower energy here. So as we go across, the energy is decreasing. What's happening to the wavelength? It's increasing, yes. So I like to think of frequency and energy as moving together. The higher the frequency, the higher the energy. So what color of light has the longest wavelength? Red. Which color has the highest energy? Blue or violet? Yes. Okay, so yes. You need to know the order of this, and you need to know that visible light is from 400 to 700 nanometers. Just definition of our wavelength. Wavelength with the Greek letter lambda looks like an upside down Y. And it's just simply the distance from the center of one crest to the next crest, or you can measure it from trough to trough. One complete wave. We measure wavelength in meters. Second wave characteristic you need to know is frequency. We'll abbreviate that with a Greek letter nu, which looks like an italicized V. Now, for some reason in physics they use an F, but in chemistry the unit or the frequency is the number of wave peaks that pass a given point per unit of time, and the unit is hertz. A hertz is simply a cycle per second. A cycle per second is written like S to the minus 1, indicating one cycle each second. You can look at this and see that this one has a higher frequency, and you also notice that what happens to the wavelength, I should use a different color, what happens to the wavelength as the frequency decreases, the wavelength increases, gets longer. Yes?
So is it the number of wavelengths?
So note that that's an inverse relationship. As wavelength increases, frequency decreases. And then speed of light is denoted with a C. All electromagnetic radiation travels at the same speed in a vacuum, and that is, you usually see it as 3 times 10 to the 8th meters per second, but we're being a little more precise here. Your book gives it to you like this, 2.9979 times 10 to the 8th meters per second. Okay, and so this shows how all of these are related. The speed of light is equal to the wavelength times the frequency. Okay, I put this slide in here just to kind of review with you. You can see that this is white light. White light contains all of the wavelengths of color. When it goes into a prism, they all have a different wavelength. Therefore, when they leave that prism, they all refract or bend to a different degree, and that's why they separate out into a rainbow. The rainbow is called a continuous spectrum, as opposed to a line spectrum. If you passed light of a different color, like say red from a neon light, then you would not get a continuous spectrum here. Instead, you would get bands of color only, a line spectrum that would be unique to that element. Okay, these are sample possible AP questions, type questions. So blue light has a shorter wavelength than red light. True or false? True, because we know red light has the longest wavelength of all the colors, right? X-rays have lower frequencies than radio waves. What do you think? Think about frequency. It's related to energy. The greater the frequency, the greater the energy. So which one's more harmful? X-rays, right? So that would be false. Number 3, microwaves have higher frequencies than gamma rays. False. Gamma rays are more harmful, therefore more energy, higher frequency. Number 4, visible radiation composes the major portion of the electromagnetic spectrum. False. We said it was only one small part of it. Basically just a plug and chug kind of problem. Photosynthesis uses light with a frequency of 4.54 times 10 to the 14th cycles per second. What wavelength does this correspond to? So we're just going to use our equation that we just got. Frequency is equal to the speed of light over the wavelength, but if we can rearrange that so that we solve for wavelength equals the speed of light over frequency, and then we'll just plug in our numbers. The speed of light is 2.9979 times 10 to the 8 meters per second, and then we'll put in our frequency, and that's our wavelength that we get. Then you should ask yourself, does this make sense? We're talking about photosynthesis, so that's visible light. Ask yourself, is this in the visible light range? Yes, because that's in meters. We said it's nanometers, but if you change this to nanometers, you're going to get 660, which is between 400 and 700, so yes. The light has measurable wave characteristics. It has measurable wavelength. It has a frequency just like waves. However, in some instances, light behaves like particles rather than waves. So light has a dual nature. You'll hear this referred to as the wave-particle nature of light, or wave-particle duality. We also know that electrons also have wave-like characteristics. What do you see, the old woman or young woman? Okay. Is there anyone that can't see both?
I don't know.
A little bit of history here. We covered this in honors chemistry, but early 20th century, light was thought of as waves because it had measurable wave characteristics. It had a wavelength, it had a frequency. But there were two aspects that couldn't be explained by the wave theory of light. One is the emission of light by matter. The way you heat something up and it glows orange and then it goes white hot. If light were waves, then the wave theory predicted that hot objects would glow with infrared or invisible radiation. It's one problem with the wave theory, with light as waves. The second problem was the absorption of light by matter, as in the photoelectric. Certain metals, photoelectric metals, will eject electrons when light of a certain frequency shines on them. You shine the light on there, the electrons are knocked off. That is the photoelectric effect. Yes. So this metal, when light shines on it, electrons are knocked off. That's the photoelectric effect. Now, what's the problem with that and the wave theory of light? Here's the problem. If red light, bright red light shines on this photoelectric metal, nothing happens. Red light simply can't produce the effect, no matter how bright it is, how intense it is. But you take a very dim violet light, and you can get electrons knocked off, a stream of electrons. So if light were waves, this really doesn't add up, because it seems that if you make the light very intense, any color of light should be able to produce the effect, because you should have a build-up, and it should be able to knock electrons off. So those two problems with light, the wave theory of light, existed. So this is what I just said. Intense red light cannot produce the effect, but dim violet light can. And that's the problem with the wave theory and the photoelectric effect. So Max Planck came up with a theory of describing energy as particles called quanta. He proposed that as matter heats up or cools down, it can't do so continuously. As in this ramp, it can't have any energy available, but instead it does it as in the stair step. It can have this energy or this energy, but not in between. So energy must be absorbed or released in chunks called quanta. Yeah. Planck came up with an equation that relates the energy of a photon to the frequency of its radiation. And E stands for the energy of a photon. This is frequency, and h is known as Planck's constant, which is equal to 6.626 times 10 to the negative 34. And this v is frequency. His equation can be used to tell the temperature of stars by measuring the wavelength of light that they emit, plugging into this formula and getting the frequency, plugging the frequency into Planck's equation, and the energy can be calculated. I'll show you how that works in a minute. So notice when you write this equation down that this is the change in energy for a system, and this is important. Energy is in joules per photon. It's the energy of a photon. Planck's constant is in joule seconds, and frequency is in cycles per second. So it basically just means that only certain specific amounts of energy can be gained or lost by a substance. Those quanta have magnitudes that depend on the substance. If you observe the frequency change, then the change in energy can be calculated. Lots of typos here. I guess I did this too fast. So Einstein used Planck's idea for a new way to think of light. Since light is energy, and energy exists in particles or chunks, he proposed that light is made of particles, and he called those light particles photons. It fixed the problem with the photoelectric effect. Right. So light can be viewed as a wave or corresponding stream of photons. Here's how he fixed the problem. Different colors of light have different wavelengths, different frequencies, therefore different energies. So if you can kind of think of red light with that long wavelength, the particle that corresponds to that is a small particle of energy. Each one of these particles of energy, one doesn't have the power to knock off an electron. It just doesn't carry enough energy to eject the electron. But violet light with a higher frequency would be a bigger chunk or a bigger particle of energy. Each one of these can knock off a bunch of electrons. So if you think of light as particles, then that explains the problem with the photoelectric effect. Does that make sense? Then Compton actually proved Einstein's theory by demonstrating that photons or particles of light could collide with electrons, producing an effect produced by, like that of marbles when they collide. And that's called the Compton effect. So he provided proof that light behaves as particles in some instances. So we can combine these two equations to get this equation. If we plug in what frequency is equal to speed of light over wavelength, then we get this equation, which will be very helpful, as you will see. We'll start with this sample problem. The blue color in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees Celsius. Then the compound emits blue light having a wavelength of 450 nanometers. What is the increment of energy, or the quantum, that is emitted at 450 nanometers by copper chloride? So we have these two equations. First, we want to plug in our wavelength to this equation, and we need to make sure that we put it in meters, since the speed of light is in meters per second. So we'll need to change nanometers to meters and divide by the speed of light. So that's the first thing I've done. 2.9979 times 10 to the 8th meters per second divided by 4.5 times 10 to the negative 7th meters, because remember, a nanometer is 10 to the negative 9th meters. So putting into scientific notation, you end up with times 10 to the negative 7th. When you crank out a number here, you get 6.66 times 10 to the 14th hertz. Take that wavelength, that frequency, plug it into E equals HV. So we're going to do that right here. Take this and multiply it by Planck's constant, and that gives us the energy of a photon produced by blue firework, copper chloride. So the change in energy is equal to 4.41 times 10 to the negative 19 joules. Now, what that means is that a sample of copper chloride emitting light at 450 nanometers can lose energy only in increments of that. That is the energy carried by a photon coming from copper chloride. That's the size of the quantum. Example number 2. Sodium atoms have a characteristic yellow color when excited in a flame. The color comes from the emission of light of 589 nanometers. A. What is the frequency of this radiation? B. What is the change in energy associated with this photon per mole of photon? So there are two parts of B. So first we'll start with A, and we'll just find frequency. We're looking for nu. So I've arranged this equation to solve for frequency, and it's just the speed of light over the wavelength. Again, remember, change nanometers to meters by multiplying by, put it in scientific notation, multiply by 10 to the negative 7th. So when you divide, you get 5.09 times 10 to the 14th hertz. That will be our frequency. Now, we will plug into Planck's equation, E equals hv, multiply Planck's constant by our frequency, and we get joules. Note that this is the energy of a photon. So that's the A part. What is the change in energy associated with this photon? When you get a number using Planck's equation, that's the energy per photon. The next part of B says per mole of photons. So 1 mole of photons is equal to 6.02 times 10 to the 23rd photons. So we'll use this conversion factor to get it into joules per mole, because the problem asks for the energy change per mole of photons. So we want joules per mole or kilojoules per mole. So we'll take our value, that's per photon, so I'll put it over photons, multiplied it by 6.02 times 10 to the 23rd photons per mole of photons, and came out with a number that gives me joules per mole, because photons cancel. We're in joules per mole. This is the same thing as 203 kilojoules per mole. New example. It takes 382 kilojoules of energy to remove 1 mole of electrons from gaseous cesium. What is the wavelength associated with this energy? First step, it says energy to remove 1 mole of electrons. We can't put this number into Planck's equation until we find out the joules per mole, or per photon. This is per mole. So that's our first equation, our first conversion. The conversion between energy and wavelength requires the value of energy to be per photon. So that's our first conversion. I took our given in kilojoules and changed it to joules by moving my decimal. Put it into scientific notation. So now that is changed to joules. And that's joules per mole, because it says energy to remove 1 mole of electrons. So joules per mole, I have to multiply by the conversion factor 1 mole over 6.022 times 10 to the 23rd photons. That will cancel moles. And now we will have joules per photon. Now we can plug that in to Planck's equation. You can't plug in a number for E unless it is per photon. So I've rearranged this equation, solving for E. And so there are the values plugged in, and then once I got this answer, I changed it to nanometers.